Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of today's lecture is Dispersion in Packed Beds, Non-Newtonian Effects. In the previous lecture, we have seen if a power law or Bingham plastic fluid is flowing through a packed bed, how to obtain expression for the frictional pressure drop, etc. Those things, the derivations, etc. Those things we have seen. We have also seen an example problem. Now, in the same packed bed, let us say if you wanted to include the effect of dispersion as well in the overall transport phenomena, then how to proceed. So, what are the things that you have to worry about? So, all those things that we are going to see, right. We are going to see an equation for a dispersion in packed bed as well. If there is a dispersion in packed bed, so how the concentration is varying because of the dispersion in addition to the because of the bulk flow, those things we are going to see and then derive an equation as well. Often dispersion is regarded as types of self-induced mixing process that arise during flow of fluids. Mechanism of dispersion, there are two different possible mechanisms in general. One is the molecular diffusion, another one is the mixing arising from flow pattern within the fluid. How does it appear? How does it occur? That we see especially in the case of packed bed now. In packed beds or porous media, true plug flow never occurs due to the dispersion. Obviously, if there is a dispersion, we will never have a kind of a true plug flow, and then because of that one, performance of packed beds would be adversely affected by the dispersion. So, why dispersion is very much essential in the case of packed bed, that we see. So, let us say if you have a column, right, and then that is packed with certain particles, regular or irregular whatever particles, right. So, now what happens when a fluid enters from the bottom, let us say it is entering like this. So, whatever the fluid element is entering, that is entering at certain high velocity. So, then it must be entering the column at certain high kinetic energy. So, when this fluid element comes and then enters the perforated plate here, so immediately it may be encountering resistance from the particle, right. When this fluid elements comes and then hits the particle because of high kinetic energy, that kinetic energy has to disperse other way. So, then what happens, a kind of rotation of the fluid elements takes place in the interstitial spaces. So, because of that one, rotation is there, that causes a kind of self-induction of a mixing in the process, mixing of the fluid within the bed. So, because of such kind of reasons, what happens, the dispersion is very much important in the case of packed beds. So, dispersion effects are more important in packed beds than in simple pipe flows because of several reasons. One of them is the contraction and expansion in flow passages in general takes place. So, in that because of that contraction and expansion of flow passages interconnecting interstitial spaces, there will be a kind of a rotational motion of the particles, and then that induces dispersion in the packed beds. That is one reason. Another reason is this radial mixing readily occurs in the flow passages or cells because of the loss of kinetic energy that fluid element is carrying before hitting a particle, and then that loss of kinetic energy induces a rotational motion in the neighboring interstitial spaces. Because fluid element enters with high kinetic energy, much of which is converted into rotational motion within the cells. Because of that one, radial mixing readily occurs in the case of packed beds, and then that induces additional dispersion. And then continuously changing velocity promotes dispersion in packed beds. In packed beds, we know that a completely laminar flow or completely turbulent flow does not appear in the entire column. At some interstitial spaces there may be laminar flow, other interstitial spaces may be there turbulent kind of thing may be there. So, that means from one flow passage area to the other flow passage area, the velocity is drastically changing, sometimes it is decreasing, sometimes it is increasing, and then because of this change in velocity, that also promotes dispersion in packed beds. Also, wall effects are also significant because of channeling through the region of high voidage near the wall. Near the walls, usually what we have the voidage or volume fraction is more, actually this voidage is also not uniform in the entire packed bed. If you take region wise if you do, right, overall volume fraction we take for engineering calculations, but if you are using especially regular non-spherical particles etc., then what happens, the voidage is varying from location to the location. So, that voidage is in general very high near the walls, right, compared to the voidage at the center of the bed, right. So, because of that one also, wall effects near the wall, that also induces dispersion in packed beds. Because of these many reasons, what happens, we have seen that dispersion is very much essential in the case of packed bed, if a column is packed with particles rather than if you are having only empty column. If there is an empty column, dispersion may be very small or may be negligible in many of the applications, but if the part of the column is packed with particles, then dispersion is going to be very large, and then one cannot avoid considering it in engineering calculation, either for the design of the equipment or for tuning of the operational parameters. So, why does it happen in the case of packed beds? Because of these many listed reasons. So, in general, what happens at low flow rates or small Reynolds number, molecular diffusion dominates in general, that we know, and then cell mixing due to the rotational motion contributes relatively very little to overall dispersion in general, right. So, this dispersion also we have seen, like because of the molecular diffusion as well as because of the flow, right. So, at low Reynolds number, molecular diffusion dominates, that we understand. The convection or contribution because of the bulk flow is very less. So, obviously under such conditions, if you have the flow rate small, that is small Reynolds number region, so molecular diffusion would be dominating, and cell mixing due to the rotational motion contributes very little to the overall dispersion if the Reynolds number is small. However, if Reynolds number is high, mixing in packed bed may be modeled by considering it consists of series of mixing cells. How to do that, all we do. So, that means at high Reynolds number or high flow rates, the dispersion is going to be significantly large, so that one has to consider appropriately. And then each mixing cell being of same size as the packing itself. So, next slide we are going to derive the equation for the dispersion in packed bed. So, for that reason these assumptions are important. So, we are assuming the packed bed is divided into several small cells in which dispersion or mixing is taking place, and those cells are also having the same shape like a column in which we have done the packing to get the packed beds, right. So, each mixing cell being of same size, and then all such cells have been assumed to be like equal size. And then finally, irrespective of mechanism, dispersion is characterized by the dispersion coefficient. So, in the case of diffusion, we have diffusivity or diffusion coefficients. When we are considering this dispersion, then we have a dispersion coefficients, and then diffusivity does not depend on the flow regime and then geometry in which the flow is taking place, etc. It does not depend on that one, but dispersion strongly depends on the flow regime and then also depends on the flow geometry in which the flow is taking place. For example, just said, if you have an empty column in which fluid is flowing, so then dispersion coefficients may be very small and negligible, but the same column, part of the column, if you pack with certain kind of material, so what happens, the dispersion significantly increases, right. So, that means it depends on the flow geometry as well, and then obviously definitely it is if it is depending on the flow geometry, definitely it will be depending on the flow conditions, whether the low Reynolds number region or high Reynolds number region, that is flow of the fluid also having the effect on the dispersion. So, in packed bed, dispersion is anisotropic except at low velocities, because at low velocities usually we understand that molecular diffusion dominates. Whatever the radial mixing that occurs in the cells, that is very small because of the dispersion or the contribution to the dispersion. The contribution to the dispersion because of the radial mixing is very small compared to the molecular diffusion at low velocities or small Reynolds number. that we know. However, dispersion, if it is not in the low Reynolds number region or low flow rate regions, it is not anisotropic, it will be having different values in different directions, right. So, molecular diffusion we have only one for a given system, diffusivity or diffusion coefficient we have only one, irrespective of the flow regime, irrespective of the geometry, we have only one. But here in the case of dispersion, it depends on the geometry, and then especially in the case of packed beds, what happens, this dispersion is anisotropic, especially beyond the low Reynolds number region. Right. If it is low Reynolds number region, in general dispersion is very small, and then molecular diffusion is going to dominate. So, that means above beyond certain low Reynolds number region, after crossing certain low Reynolds number region, dispersion is going to be different in different direction. That is, it is going to be different in radial direction, it is going to be different in axial direction if you are taking a cylindrical column for packing of the bed. So, that is what it means by it is anisotropic. So, that is dl is dispersion coefficient in axial or longitudinal direction, and dr is dispersion coefficient in radial directions. Okay. And these are very different from each other, especially when the Reynolds number is beyond the low Reynolds number region, or the flow rate is not in the low velocities region, but high velocities region, right. So, they are different from each other when the velocity is more than the low velocity region or small Reynolds number region. So, when the Reynolds number region is higher, then or when you go beyond the streamlines region, then what we have? We have these dl, dr are very much different from each other. Dispersion is considered to be linear in general, and then rate of dispersion is proportional to the concentration gradient multiplied by the corresponding dispersion coefficient. It is defined slightly similar way as we define molecular diffusion, right. So, where here dispersion whatever is there, rate of dispersion whatever is there, that is proportional to the concentration gradient. Like in molecular diffusion, the flux is proportional to the concentration gradient. Here also rate of dispersion is proportional to the concentration gradient, and the proportionality constant is known as the dispersion coefficient. It changes in the different direction, all three direction of the geometry, it may be having different dispersion coefficients. Let us say if you have a cylindrical packed bed, then dispersion coefficient in longitudinal direction and dispersion coefficient in the radial direction are going to be different. Okay. So, unlike in the molecular diffusion coefficient DAB, as I already mentioned, DL, DR are strongly dependent on flow regime and bed geometry. Okay. So, dispersion coefficient is analogous to eddy kinematic viscosity, which is not same in all the direction, it varies from direction to direction. So, now what we do? We do derivation of differential equation for dispersion. So, very first assumption in this case is that whatever the column is there, if the column is cylindrical column, then whatever the packed bed is there, that we are dividing into the small cells which are also in cylindrical shape, and then all those cells are having same size. Okay. So, cells of same shape and size, this is one essential important assumption, right. Another one is that these cells are porous, because our whatever the packed bed is there, that is having that is one type of porous media, and then interstitial spaces are there. So, the entire bed is not completely packed, some of the volume fraction is void space is there. So, because of that one we have to take these cells also porous. In general, whenever we do the momentum or mass balance for the given geometry, we take that walls are solid no slip walls kind of thing. But now this is packed bed which is like a porous media. So, then cells we have to take, they are as porous, right. So, that these two are the important essential assumptions in this derivation. Other than these two, after having these two, and then it is simply what is the rate of dispersion at the inlet what is the rate of dispersion at the outlet, what is the net rate, etc. Those things we have to mathematically represent and then do the substitution in the overall balance equation. So, that is all mathematical procedure, right. So, now these two are the very essential, and then after that we can understand schematically what does it mean by exactly. So, differential equation for dispersion in a cylindrical bed of voidage epsilon should be derived now. So, this is the cell that I was mentioning. So, we have taken porous packed bed, okay, or packed bed we have taken where interstitial spaces are there, and then the packed bed we have made in a cylindrical column by making some kind of packing material. So, that is the reason that packed bed whatever is there. So, let us say this packed bed. So, now this packed bed we have divided into several cylindrical cells, because this bed itself is a made in a kind of cylindrical column like this. So, what will happen? So, then we have to have a kind of a bed cells also cylindrical type, and then these cells they are also having the equal size and then same shape like a bed like a column in which we have done the packing. So, then we have this representation. So, now this is the representation of such cells of same size and shape, and then they are porous in nature. Shape we have taken cylindrical cell because the packing we have done in the cylindrical column, right. The height of this cell is dl, the inner radius of the cell is r, outer radius of cell is r plus dr. So, that thickness of the cell we can take as dr. The material, the fluid is entering at V0 velocity at the bottom and then leaving from the top. Okay. The concentration of the material that is entering is C. So, how this C variations in C are occurring because of the dispersion, that is what we are going to derive mathematically, right. So, material balance over annular element of height dl, inner radius r and outer radius r plus dr should be used now. Let C be the concentration of reference material, and it is function of obviously the space, time and then dispersion coefficients, right, as well as the voidage. Okay. So, it is a function of axial position L, radial position r, that is what mean by it is function of space, and then it is function of time as well. In addition to that one, it is also function of the dispersion coefficients dl and dr. Okay. dl is the dispersion coefficient in the axial direction, dr is the dispersion coefficient in the radial direction. We understand that if the flow Reynolds, if the flow rate is higher, if we are not in the streamline flow region, then these dispersion coefficients are anisotropic. We have more than one dispersion coefficient and then they may be different in the different directions, unlike molecular diffusivity DAB. DAB is same irrespective of the flow geometry and then flow region, but here it is not like that. Okay. So, pictorially we write quantities that are entering here. So, the rate of material that is entering at the inlet because of the flow is this one, 2 pi r dr V naught C. 2 pi r dr is the cross section area of the cell through which the material is entering, and then V naught is the velocity at which entering, C is the concentration. This is because of the motion, bulk motion. Okay. And then if the same, if it is, it may, because the mechanism, two mechanisms are there here also, molecular diffusion mechanism or molecular mechanism as well as the bulk motion mechanism that we are having. So, this is because of the bulk motion. Because of the molecular mechanism, the rate at which material is entering is 2 pi r dr and then epsilon, because it is a porous, multiplied by dl dou C by dou L. dl dou C by dou L, actually dl minus dou C by dou L, that minus we have written here, right. Okay. So, dl, why not dr, why not dr, why dl here, because it is axial direction we are taking, axial direction components we are taking, that is the reason it is dl. So, similarly at the outlet, what are the corresponding quantities they are leaving because of the convection and then because of the bulk motion and because of the diffusion, because of bulk motion, this is the component, that is 2 pi r dr V naught. C, in C there is a change of delta C, that change in delta C we are writing dou C by dou L dl. Okay. And then similarly, material leaving because of the diffusion is 2 pi r dr epsilon dl is as it is. What we have, dou C by dou L is as it is, it is having. The change in C is change in dou C by dou L we have to write, that change in dou C by dou L is nothing but dou by dou L of dou C by dou L multiplied by dl. So, that is dou square C by dou L square dl, that is the addition. The change in concentration at the outlet because of the diffusion is dou square C by dou L square, that is what is there. So, that we have written here, right. Now, this is in the axial direction. Now, in the radial direction there is no convection, whatever the bulk flow is there, that is there only in the axial direction, right. So, bulk flow component or the rate of the material entering because of the bulk flow will not be there in the case of radial components, because the bulk flow is there only in the axial direction. In the radial direction we have only diffusion or molecular mechanism is taking place. So, what is the rate at which the material is entering at r is 2 pi r dr epsilon, and then because of the molecular diffusion dr dou C by dou r. Why dr here? Because now the diffusion, now the dispersion we are considering in the radial direction, and then the change in concentration also in the radial direction, that is the reason dou C by dou r. Okay. So, then what is the rate at which it is leaving at r plus dr? It should be 2 pi, in place of r we have to write r plus dr, and then dr epsilon dr as it is, and then change in dou C by dou r. Change in dou C by dou r is nothing but dou by dou r of dou C by dou r and then multiplied by dr. So, that is dou square C by dou r square dr. So, that is the component, that is the rate of the material that is leaving at r plus dr because of the molecular diffusion in the radial direction. Okay. So, in the pictorially we have shown all the components here. So, now all this should be balanced by the total overall accumulation. So, inlet minus outlet in the radial direction plus inlet minus outlet in the axial direction, that you do, then whatever the entire all the summation is there of two components, that should be equated to the overall accumulation. Okay. So, that is 2 pi r dr dl dou C by dou t. Okay. So, then when you do, then you get the final equation. So, that we are representing here. So, rate of entry of reference material due to flow in axial direction is this one. Same because of the then corresponding exit of material due to the flow in axial direction is this one, that we have seen picture in the picture. So, net accumulation rate in element due to flow in axial direction, due to flow only. So, this 1 minus 2 if you do, this is what you get, that is what we have written in picture figure as well. Similarly, rate of diffusion in axial direction across the entry inlet, this is what we have written, and then corresponding rate of diffusion in axial direction across the exit or outlet boundary is this one, that is what we have written. After simplifying this one we got. Then net accumulation rate due to diffusion in axial direction should be across, that is across inlet and outlet boundaries, that is equation number 4 and 5. When you do, you get this equation, right. All this pictorially I have shown these quantities, we are again writing here. So, now diffusion in radial direction at r we have written this one, and then corresponding diffusion rate at r plus dr, the other side of the boundary we have written this one. After simplifying we get this equation. So, net accumulation rate due to diffusion from boundaries in radial direction from r to r plus dr is equation 8 minus equation 7, that you do simply you get this equation, right. So, now dr we are taking very small, so then this term may be cancelled out, okay, and then these two terms we can combine and write like this term, right. Total accumulation rate in the overall cell is 2 pi r dr dl epsilon dou C by dou t. total volume of the cell multiplied by epsilon, because whatever the transfer of the material is taking place because of the dispersion, that is taking only in the epsilon void space fraction only. So, that the total volume of the cell multiplied by epsilon, and then that multiplied by dou C by dou T, that will give total accumulation rate. So, now this total accumulation rate should be balanced by net accumulation rate due to flow in axial direction plus net accumulation rate due to diffusion in axial direction plus net accumulation rate due to diffusion in radial direction, that all the quantities we have written in previous slides. Okay. When you do this material balance, 2 pi r dr dl epsilon dou C by dou T is this one. This is the net accumulation in the axial direction because of the bulk flow, and then this is net accumulation in the again axial direction, but because of the molecular mechanism, and then this is net accumulation in the radial direction because of the molecular mechanism. In the radial direction there is no bulk flow is dominating in only axial direction. So, now this entire equation you divide by 2 pi r dr dl epsilon, then you get simply dou C by dou T plus V naught by epsilon dou C by dou L is equals to dl dou square C by dou L square plus 1 by r dr dou by dou r dou C by dou r. This is what you get, and this equation is nothing but change in concentration of reference material in a packed bed because of the dispersion. It is similar like our species concentration equation that we have derived for mass transfer part. Okay. So, but only thing that here whatever the change in concentration are there, that because of the dispersion and then bulk motion only we are taking into the consideration. So, now here at what velocity you are allowing the material to flow, that in general you know. You also know what is the epsilon voidage of a bed that you have made for your real life situation, right. So, if you wanted to find out the change in concentration with respect to the space and time, that is C as function of R, L and T, then what you should have? You should also have the information of dl and dr, then only you can use this equation in order to know the change in concentration because of the dispersion. Otherwise, this equation is as useless as nothing has been done. So, the importance of this equation depends on how effectively are you going to measure this dl and dr for your system in which you are going to apply this equation. Okay. So, that we see now. Now, this is in general done. Let us say if you wanted to find out dl, dispersion coefficient in the axial direction. So, you take a tracer element and then you release in the axial direction only like this, without it any shape variations in the radial direction. Shape variations of this tracer element should not be there in the radial direction, it should go in the axial direction, such a way that you have to measure this. You have to release this tracer element and then measure the change in shape along the axial direction as well as the change in shape with respect to the time. So, longitudinal dispersion coefficient, if you wanted to obtain, inject a pulse of tracer into the bed in such a way that radial concentration gradient are eliminated. These are the pulse of tracers. So, then the concentration gradient in the sense that shape in change in shapes. The shapes there should not be change in shape in the radial direction, whatever the change in shape is there, that should be there only in the axial direction. That means only concentration gradient should be there only in the axial direction, such a way you have to inject. So, then measuring the change in shape of the pulse as it passes through the bed, you can find out, you can measure that one. So, that means dou C by dou R is equals to 0 in equation 12, previous equation. So, that means dou C by dou T plus V naught by epsilon dou C by dou L is equals to dl dou square C by dou L square. So, C you are measuring, that is what, measuring the change in shape of the pulse that is passes through the bed, that means dou C by dou L you are measuring, and then you can get the dou square C by dou L square as well if you have dou C by dou L, right. So, then similarly dou C by dou T also with respect to time you can measure. So, then dl you can find out because V naught epsilon are known. Okay. So, values of dl can be calculated from change in shape of pulse tracer as it passes between two locations in the bed. Okay. So, then you can get dl by solving this above equation 13, right. So, for gases in general at small Reynolds numbers, Peclet number increases linearly with Reynolds number, so that Pe is equals to KRE, K is the proportionality constant for the time being. Okay. So, usually this is the reality from the experimental results. When the Reynolds number is very small for gases, Pe increases proportionally with Reynolds number. So, this is the relation, Pe is equals to KRE. So, Pe for the packed beds is nothing but V naught d by epsilon dl is equals to K. Re is nothing but V naught d rho by mu. So, now right side you divide by dAb and multiply by dAb and then rearrange, so that rho dAb by mu and then V naught d by dAb you have two terms. This rho mu by rho dAb is nothing but Smith number. So, then rho dAb by mu we can write Smith number inverse, right. So, from this equation Smith number divided by K epsilon is equals to dl by dAb. So, that means for gases system usually Smith number is known because mu, rho, dAb etc. are known. From experimental results this K is known in general. For any gases system dAb is known or you can measure, right. So, then from this equation you can find out what is dl, especially for gases at small Reynolds number regions, right. So, dl by dAb is in general constant which has a value of approximately 0.7. So, Smith number is approximately constant for gases in general, it does not vary much from points, it is within 0.1, 0.5 to 0.7, 0.8 region, in that region only. And then voidage of randomly packed bed is also usually 0.4 or between 0.4 to 0.5. So, obviously this dl by dAb from this equation 14, that is also going to be constant, and then for most of the gases at low Reynolds number this dl by dAb is found to be 0.7. So, that means for any gaseous system if you know dAb, dl you can find out by multiplying dAb by 0.7, and then it is consistent with the assumption. What is the assumption? That at small Reynolds number molecular diffusivity dominates compared to the radial mixing etc. or dispersion. So, that means if dl is 0.7 times the dAb, that means dAb is having higher contribution compared to the dl. At high Reynolds number, obviously in packed beds as we have seen, the critical Reynolds number for transition from laminar to turbulent flow is in general 5 to 10. So, beyond 10 it is considered as the high Reynolds number or turbulent flow region in the packed beds. So, at high Reynolds number Re greater than 10, Pe becomes approximately constant as per the many experimental observation, especially for the gases. So, from Pe versus Re plots for dispersion in packed beds, we can have this whatever the V naught d by epsilon dl is approximately 2, that Peclet number is approximately 2 at high Reynolds number, that is constant in general. So, from here we can get dl is equals to half V naught d by epsilon, right. So, you do not even need to know the diffusivity if the Reynolds number is high in order to know the dl. If in order to know the dl at high Reynolds number region, you do not need anything including the diffusivity is also not required. Only thing that you need to know what is the velocity at which you are releasing the fluid material, what is the voidage, and then what is the size of the particle that you have used for the packing. In the intermediate range of Re, people found these two contributions at low Reynolds number and then high Reynolds number, whatever the contributions are there, they are additive, and then people have written dl is equals to 8 dAb plus half V naught epsilon of V naught d by epsilon. So, this is the contribution because of the high Reynolds number, this is the contribution because of the low Reynolds number, and then intermediate range, these two are added together. So, similarly radial dispersion coefficients, if you wanted to obtain, what you have to do? You have to inject a steady stream of tracer at the axis and measure the radial concentration gradient across the bed. Now, at certain middle portion at the axis, at the central axis, what you have to do? You have to release this same tracer, pulse of tracer, but how do you need to release? You have to release such a way that the change in shape should be there only in the radial direction, it should not be there in the axial direction. So, that dou c by dou L etc. can be taken 0, and then you can find out what is the dr from the dispersion coefficient equation that we have derived. So, we understand that molecular diffusion dominates at low Re. So, ratio of dl and dr equal to approximately 0.7 times the molecular diffusivity in general, if you combine both. The previous expressions we have done only considering dl. Now, you have to considering both dl and dr. It is found that dl by dr is approximately 0.7 times the dab from the experimental results. At high Reynolds number, people found this ratio dl by dr is approximately 5. So, in the case of high Reynolds number region, the ratio is constant, whereas in the case of a low Reynolds number region, the ratio is not constant, it is some constant multiplied by the diffusivity of the system, that is 0.7 dab. Right. Experimental results for dispersion coefficients in gases show that they can be satisfactorily represented as Peclet number expressed as function of Re, but in the liquids case, in the case whatever previous slides we have seen, that is for the gases. In the case of liquids, usually Schmidt number varies because the viscosity density of the liquids are from one liquid to the other liquid, variations may be large. Right. For the gases, variations in the viscosity and their density values are very small from one gas to the other gas. That is the reason usually Schmidt number range for gases is very narrow, so then we can take the constant. But in the case of liquids, this rho, dab, mu etc., they are not they are changing by higher magnitude from one liquid to the other liquid. So, because of that one, this Schmidt number is in general variable and generally about 3 order of magnitudes greater than that for gases. For the liquid case, when the experimental results are plotted, Peclet number versus Reynolds number, that indicated that at small Reynolds number, small in the sense Re less than or equals to order of 10 power minus 2 or 10 power minus 3, such small Reynolds number, Peclet number does not show any variation or only little variation, and it is order of unity. Comparison of these results with the corresponding ones for the gases shows that effect of molecular diffusion in liquids is insignificant at Re up to order of 10 power minus 2, 10 power minus 3 or less than Re is equals to 1. Now, finally, before ending this lecture, what we do, little literature information for dispersion in flow of shear thinning liquids through packed beds. So, Wen and Im reported few results on axial dispersion coefficient dl under the following flow conditions: weakly shear thinning polymer solutions, packed bed with a glass piers of such an diameter and then such diameters, voidage of 0.4 and 0.5, and then experiments they conducted in the Reynolds number range 7 to 800. Right. They are all experimental results we are discussing now, because we wanted to see the effect of non-Newtonian fluids in the dispersion in packed beds. Okay. So, in these people, they have developed this correlation for the case of Newtonian fluids. Say the voidage diameter of particles used for packing keeping same, they have taken Newtonian fluids and then have done the experiments in order to find out the dispersion coefficients etc. So, they found this correlation is suitable, right. However, when they change the fluid to weakly shear thinning fluids, they found the same correlation is still valid, but with Reynolds number defined like REMR. This is similar like REMR or REPL that we have seen previously, and then Peclet number is V naught d by dl. They have not taken epsilon in the definition of a Peclet number or Reynolds number. Subsequent experimental work carried out with a wider range of n between 0.53 to 1, and then but a smaller wide edge range, and then very small particles of glass beads, but at Reynolds number order of 10 power minus 3, so that the second term in their correlation is negligible. So, that is what they found, right. So, in this correlation later on they have done experiments by taking very small values of Reynolds number. If the Reynolds number is small, so Reynolds power 0.48, and then that is again multiplied by 0.011. So, if Reynolds number is small, so then obviously Peclet number is going to be constant for the case of a small Reynolds number case. That also they have done. But under these conditions, Peclet number showed a weak dependence on the power law index, that is Peclet number is decreasing from 0.2 to 0.1 when n is decreasing from 1 to 0.53, right, thereby suggesting greater dispersion in shear thinning fluids. Okay. So, finally, mass transfer in packed beds. Kumar and Upadhyay measured rate of dissolution of benzoic acid spheres in and cylindrical pellets. So, they have taken benzoic acid particles in two shapes, spherical and cylindrical shapes, and then they have done the experiments in CMC solution, dissolution or dispersion of these pellets in CMC solutions having n 0.85, and then they have used a plug flow model and proposed a correlation for correlation for Jm factor, and then that is given by this equation, okay, where Re prime is the modified Reynolds number that is defined as this one, same like a packed bed case yesterday that we have seen, where mu effective is m prime 12 V naught 1 minus epsilon by d epsilon square whole power n minus 1. This definition is same like yesterday's class, whatever we have studied for the frictional pressure drop calculations by Kumar and Upadhyaya. Here Kc is mass transfer coefficient and Schmidt number is defined as a mu effective by rho dAb. Effective viscosity they have taken in order to define the Schmidt number that have been used for the Jm correlation. And the range of condition of their experiments are given here. They have taken only one n value, and they found that their correlation having within plus or minus 10% of mean error. So, above correlation has subsequently been confirmed independently by Vransky and Stoeger, and they found that Jm factor over predicts at lower Reynolds number regions. Okay. And these people considered most of the data in the literature and proposed the following modified correlation for the Jm factor, which is different from the Kumar and Upadhyaya. It offers more improvement over the correlation of Kumar and Upadhyaya that we have shown in the previous slides, especially in the low Reynolds number region. However, no analogous heat transfer results have been found in the literature, especially when you use non-Newtonian fluids flowing through packed beds. References: the entire lecture is prepared from this book Chabra and Richardson. However, the derivation of the equation that we have done, that has been taken from Coulson and Richardson book volume 2. Other useful references are provided here. Thank you.